Here's your question. 3 choices. If there's a log in a stream directly above the log, would you see the surface of the stream bump upwards, stay flat, or dip downwards? So post your comment down below. What's your first instinct? You've seen water before. What does it look like? And to me, I don't think I've ever seen a stream with a bump or a dip in it. So for me, I think flat. That is my first instinct for what should happen in this system. But as is often the case, my first instinct is wrong. And this is something that's hard to see out in the wild because in real world systems, there's so many complicating factors going on. But this is a case that's very easily reproduced in a lab. And you can see that the correct answer is actually the dip. If you want to go ahead and write down that you called it the whole time down in the comments, no one will ever suspect you waited to hear the answer before you made your post. And so good news is that you don't actually just have to memorize this. You could actually figure out this answer yourself using the Bernoulli equation. So consider the top surface of the water as a streamline from a point A before the bump in the water to point B directly above the bump. Now suppose that there was a similar bump on the top of the water. Let's look at what happened to Bernoulli equation in that scenario. The Bernoulli equation has 3 components: pressure, velocity, and elevation. The pressure is the same at point A and B. They're both at atmospheric pressure. If the bump at the water is the same height as the bump of the log, then velocity of the water would not change because there'd be the same area in front of the bump as during the bump. So if the area is the same for the flow rate to be the same because of the continuity equation, then velocity would be the same. But elevation would have increased. The water would have gone up in elevation, and that makes a problem. If pressure is the same and velocity is the same, elevation can't increase. That would give the system more energy than it had at the beginning. Bernoulli equation is a variation of the conservation of energy. So it clearly can't go upwards because that would violate conservation of energy. So why can't it stay flat? It seems like every river and creek that I've ever seen has just been flat, no matter what sort of rocks or logs or anything are on the bottom. Pressure at A and B is still the same, atmospheric pressure. Elevation is the same at A and B because it hasn't changed in height in this scenario. But because of the bump down at the bottom and the top staying at the same height, there's a compressed area. The continuity equation says you need the same flow rate through A and B. And if B is in a smaller area, it must be moving at a faster velocity to maintain the same flow rate. If pressure and height are the same, but velocity increases, that violates conservation of energy, right? Bernoulli equation would not be upheld. And in the real world, there's actually all sorts of other complicating effects happening, waves and things like that, to just make it harder to see that the correct answer is actually the dip. So from point A to point B, the pressure is the same, atmospheric pressure. Elevation decreases because of the drop in height, but velocity increases. Because of the drop in height, the flow has to increase in order to make it through a smaller area to maintain the same throughput. Very counterintuitively, this is very weird, a bump at the bottom of the water would actually cause a dip in the top of the water so that the whole thing contracts almost like a nozzle and the water goes faster. And that energy has to come from somewhere. If it's going to speed up, that energy has to come from height because it can't come from pressure if it's exposed to the atmosphere. So the height has to go down in order to allow the water to pass through more quickly. Weird, but sets us up perfectly for this example problem. If we were actually able to measure the size of this dip, so this must be in some kind of lab experiment, you probably couldn't actually measure this in the real world. What is the volumetric flow rate through this system? Start off by writing the Bernoulli equation assumptions that we have to ignore viscous effects, that the system is at steady state, and that the system is also incompressible. And we're also going to be using a continuity equation, and the big assumption for there is that we're going to assume that the control volume is steady, so that mass flow rate in is going to equal mass flow rate out. Write down the Bernoulli equation, and I'm going to choose my points A and B again on the top surface. And what that allows me to do is to cross off the pressure terms because they're both exposed to the same atmospheric pressure. And since it's the same fluid at the same temperature, the specific weight is also going to be the same. And I like working with the head version of the Bernoulli equation. There are other versions in terms of pressure or whatever else, but this is the one I like. So I start plugging in numbers, see where we stand. And of course, right off the bat, I made 2 immediate mistakes. And I'll pause and ramble here for just a second for you to look at the equation I just wrote. Do you spot them? Do you spot 2 mistakes? First one's gravity, really dumb mistake. 9.81 is for metric units. English units should be using 32.2 feet per second squared for gravity. The other one's a little bit harder to spot. It's the height at point B. Should actually be 3.5, not 3.3. If I'm measuring heights from the very bottom of the creek, not the bottom of the bump. All right, so fixing those, that still leaves us with two unknowns, right? Both velocities are unknown. So we'll move to the second equation, right? If we have one equation with two unknowns, we need a second equation. It's gonna be the continuity equation. Mass flow rate in at A equals mass flow rate out of the control volume at B. Mass flow rate is rho AV, density times area times velocity, but since it's the same water at the same temperature at both points, density for this problem will be constant. So I can really just say that QA equals QB, that the volumetric flow rates are equal to each other. And so velocity times area equals velocity times area. So now two equations, same two unknowns, and now it's just algebra. You can solve for VA or VB, whichever one. I'll start off by just isolating VA and then plugging that into the original Bernoulli equation, and you get to a velocity B at about 10 feet per second. And since the final answer is flow rate, not velocity, multiplied by the cross-sectional area, where this time I am using 3.3, not 3.5, because at point B, the cross-sectional area is that 3.3 deep. Final answer, 66.3 cubic feet per second, volumetric flow rate, Q. It's a really weird problem, very counterintuitive to get a dip instead of a bump. But now that you've seen it once, you won't be tricked by it in case you see it later in one of your classes. And maybe if you're ready for something a little bit more straightforward, a little bit easier, you can watch some more Bernoulli continuity equations over here in these other videos on the screen. These are way more straightforward. It'll be a nice little change of pace after this video, something kind of relaxing, a little bit easier, but still really good practice.